and welcome to part 2 of the Chapter 3 videos where we're going to go through section 3.2. We're going to start with these measures of dispersion, and that's really all that we're going to get to in this video are the measures of dispersion. And we're going to start with the most basic one that should also be very familiar, which is the range. And of course the range of the data values is just the difference between the largest data value and the smallest data value. So going back to the same data set from before, we have these 7 values of the commute times, and to find the range we should just find the largest data value in here, which is 43, and then the smallest data value, which is 13, and we will subtract them. 43 minus 13 is 30, so that would be the range. It's very simple, very familiar. And then the next one coming up, we're getting into the ones that we're going to use very commonly, especially the standard deviation. But the standard deviation is already very heavily based on the variance. And so we would discuss first, which it is a little bit more simple to calculate, only a little bit, but the variance. And the way that we find this one, we're going to be going back to this summation notation. And here we're getting, of course, the abbreviated version. But I'm going to take the population variance here and just break down some of this notation, what's going on. We're adding up a bunch of things. That's why we're adding up all of these elements that are going from 1 up until the size of the population, which is the difference between each data value, and mu, of course, is the population mean. So we're finding the differences between the individual data values and the means, or the mean rather, there's only one mean, squaring it, squaring this difference, and then adding them up. And once we're done adding up all of these squared differences, we're going to divide by the size of the population. So we end up with something that feels a little bit like an average, because if you think about how you do an average, you add up a bunch of things and then divide by how many things you added. But since we're not just adding the individual data values, we're adding the differences between the data values and the mean. What we're ending up here in terms of the variance, it resembles something like the average distance that the data values are from the mean. And in order to make it actually resemble a distance even more, we introduce this idea of the standard deviation. And the standard deviation is we take this thing and then this variance to be specific, and we just take the square root. So here the standard deviation is defined as the square root of the variance. And this, of course, it resembles a distance, because if you think about what the distance formula is, it is a square root of squared differences. If you can remember, between these points, if you have a point like x1, y1, and then you have another point like x2, y2, then the distance between these points, it's given as the square root of the difference of the x values squared plus the difference of the y values squared. And then it should be pretty easy to recognize that this looks the same as how the variance was going to look after we take the square root of this one. Because this, if we break down what this summation means, we're going to take all of these differences and square them and then add them together. And so we're going to end up with, I'm running off the sheet here, but then it's going to go to the last one. And it's kind of this multi-dimensional distance once we take the square root of this one. So that's the idea for the standard deviation. It's the sort of like the average distance that the data values are from the mean. And then it should be clear why this is called a measure of dispersion, telling us how much the data are spread out, how far they're spread away from the mean. And here we have predictably the same data set, the same 7 numbers, and we're going to find the population standard deviation. Now these are still in my calculator in list 1, and the standard deviation, population and sample standard deviations, those were things that are in 1-var stats. So I'm going to do 1-var stats for list 1, and the population standard deviation, of course, it's this one over here that has the sigma. The S corresponds with the sample standard deviation, and that is going to give us 9.56. And then we have a couple of properties here. Not a couple, we have 7 different listed properties over here. But these properties, they're interesting, but we're not going to focus on them too much. Just a couple of things, like here, number 3, the outliers can cause the standard deviation to increase dramatically. That's giving us a clue that standard deviation is not a resistant measure. And then we also have a couple of ideas, like the fact that the standard deviation, it's always positive. And of course that makes sense, since the standard deviation has to do with the squaring. Whenever you square a number, it becomes positive. And so for sure the standard deviation is always going to be positive. And then a way to interpret the magnitude of the standard deviation. For example, since the standard deviation is the distance from the mean on average that the data set has, whenever the values are close together, we're expecting to get a small number for the standard deviation because the data tend to be close or have a very small distance from the mean on average. And we also saw how to find the standard deviation on the calculator, and so I'm just going to zoom past that one. Now we've got a little data set over here that we can find the mean and standard deviation for. I'm going to go ahead and put these into one of my lists. And I've chosen to place them inside of list 4. Now, of course, we can find the mean and the standard deviation at the same time just by going to stat calc. I'm going to get the 1-bar stats for list 4. And then I would just be careful to pick out, in this case, the standard deviation for the sample, since 1-bar stats gives us both options. We have X bar, it's given to us, it's in the first step, the first value that's given to us. I'll just give the whole value there, not bothering to round. And then the sample standard deviation, I'm going to round this one to two decimals just arbitrarily. It looks like a nice rounding, 2.01. And now this next example, these data sets are rather large, and I want to use StatCrunch for these large data sets, but I would recommend anybody to try these, answer a couple of questions over here, and I am going to move on to this idea, which is the empirical rule. This is a very important concept for this chapter and also for just the whole thing about statistics. The empirical rule, we're going to see, these are approximations. That's why we're saying for each of these statements here something about approximately. We will learn how to find the exact values a little bit later when we talk about normal distributions. But the empirical rule, it's getting into this idea of making predictions about probabilities using the distributions. And so the empirical rule, what it states is that if the distribution is roughly bell-shaped, and I will give my best attempt here at drawing a bell-shaped curve. Into this picture, we're going to see here in this example how we are going to use the empirical rule with these bell-shaped curves, but always we are having the same idea for drawing these pictures. These little markings are not just drawn randomly. What we have in the center here, this marking represents the mean, and then each marking that follows are going by increments of standard deviations. So this particular distribution, it has some standard deviation that's just called sigma, and if we take that standard deviation and we add it to the mean, we will get this first increment. So this is the mean after we add the standard deviation to it. And then if we add another standard deviation, so if we've added the standard deviation twice, we will get the next marking, and so forth. And it is the same coming on this negative side. If we subtract the standard deviation from the mean, so we go by one standard deviation to the left, we will have the mean minus the standard deviation. That will be the next marking. And that's how I'm going to label these increments. We can subtract the standard deviation twice, we can subtract the standard deviation 3 times, and we could also add the standard deviation 3 times to get this marking. And this is going to be, I don't want it to look like 36, so I'm going to try that one again. This is going to be a very standard way to make these graphs, that we are going by increments of the standard deviation on both sides, with the mean being in the middle. And the empirical rule, it says that the data that lie within one standard deviation of the mean, that this should be 68% of the data. The same thing if we take what is in between 2 standard deviations of the mean. This is getting to where we're having a lot of the data in here. That's 95%. And then all of the data that are within 3 standard deviations, that's going to be 99.7% of the data. So almost all of the data, just missing a fraction of a percent, are going to be within 3 standard deviations of the mean. And that is true for any type of a distribution that's roughly bell-shaped, but in particular things that are normally distributed, which would be some common measures. If you think about the heights of males, for example, the heights of males in the United States, it would be roughly a normal distribution, and so it would follow the empirical rule. And it would be very rare, for example, to find somebody who's more than 2 standard deviations away from the mean, either on the shorter side or on the taller side. And that's what we get from the empirical rule. In particular, I say that it would be rare because we use a standard of a 5% probability as being something that would be considered rare or unusual. And I'm going to carry on with this example of how to use the empirical rule in an application. Something else that's normally distributed are the IQ scores of adults. And so we'll see it as a recurring theme that we can use IQ scores as an example of a normal distribution, where the mean, so that should be the value that's in the middle, is 100, and then the standard deviation is 15. So if we add increments of 15 to 100, I will label those values there. So 145, it's 3 standard deviations more than the mean. And then I will go by increments of 15 less than the mean, and so I'm getting 85, 70, and 55. And now we can answer some of these questions, like what percentage of adults have IQ scores between 55 and 145? And we've got those values actually listed here. 55 is 3 standard deviations less than the mean, and 145 is 3 standard deviations more. So the question is, how much of the data is in between those two values? And by the empirical rule says that there should be 99.7% of the data that are between 3 standard deviations, or within 3 standard deviations of the mean. And then I'm going to get rid of these markings because we're about to have to ask a different question in a second. But the next one, we can keep this same threshold, the 145, because we're answering this question, what percentage of adults have IQ scores greater than 145? So now we're looking at this little tail over here. Now keep in mind that the big bulk of data that's in the middle is 99.7% of the data. And of course the whole curve together, everything that's underneath the curve going towards infinity on this side, of course nobody has an IQ of infinity, and going this left side towards 0, nobody has an IQ of 0, but it's getting less and less probable as the IQs go down. We end up with these little tails that are making up basically the other 0.3%. So if we were to add these two tails, they're everything that makes up 100% besides 99.7. So these are 0.3% together, and each one of them, since there's a symmetry about this distribution, each one of these tails has half as much as this, and so this tail should be half of 0.3%, and that should be 0.15%. And so that's actually going to be the percentage of adults that have IQ scores greater than 145. It's 0.15%. And now we will move on to another example. We can answer some more questions that are going to have to do with the empirical rule, so I'd still like to use this nice bell curve that's drawn for us. I'm just going to relabel it because we're about to have a different distribution that has a different mean and a different standard deviation, so we will just label these markings a little bit differently. You see, this time the mean is going to be 50, and the standard deviation is 5. So every time we go by increments of the standard deviation, it's increments of 5. And then we can go on the side where we're going less than the mean by the standard deviation, so still increments of 5. And we don't have a context here of what variable we're measuring, but these are just going to be the data values, so we'll talk about it abstractly. But we can still figure out, since we know that it has a normal distribution, and in general that means that it's going to be bell-shaped, we can figure out what percentage of these values would we expect to fall between 40 and 60. And if we're going to use the empirical rule, we should hope that this has something to do with standard deviations, and of course it does, because 40 and 60, these were a couple of our values that we had on this one. So 40 is 2 standard deviations less. That was the mean minus 2 standard deviations. And then 60 is 2 standard deviations more. And according to the empirical rule, the data that are within 2 standard deviations of the mean, that should be 95% of the data. So we can just answer that one right away. And what about this question? This is going to be still just using the empirical rule. What percentage of these values would we expect to fall between 45 and 55? So now we're just getting a little bit closer to the mean, but it still is by an increment of standard deviations. It's within 1 standard deviation of the mean. So we're getting this middle group that is within 1 standard deviation of the mean. By the empirical rule, that should be 68%. And now at least 99.7% of the values will fall within what 2 numbers? It should be within 3 standard deviations, and so those are our markings out here, which are 35 and 65. And that's going to do it for this video. I will see you in the next video where we will begin with 3.3, and thank you all for watching.